Okay, so we're gonna use the method of exact solutions to solve this, and since it's already in the standard form, we can test if it's exact. That would be the first step. So to test if it's exact, you remember what to do? The partials. So this is your m here, and the one that multiplies the derivative is your m, and this will be exact if and only if partial of m with respect to y is equal to partial of n with respect to x. Okay, so let's go ahead and find what that is. So partial of m with respect to y. So you fix the x, you differentiate with respect to y. So if x is held constant, you would get 6xy squared. Likewise, for dn over dx, you hold the y constant like a number, and you differentiate with respect to x. Clear on that? So we get 6xy squared. Hallelujah! Indeed, indeed they're the same, so therefore exact. So we have an exact differential equation, right? Now, what that means, if it's exact,
If this is basically you can treat that as an x component and that as a y component.
yeah, that just means that there's some function, potential, whose gradient is the actual components of the differential equation.
It's m and n.
So what I'm saying is that partial with respect to x is m. What that means that df over dx is equal to 2xy cubed, and we can pretty much cross multiply df equal to 2xy cubed dx, and now we can integrate both sides, and then we can get f function of x and y whose gradient will be that we are looking for is equal to x squared y cubed plus the constant of integration in this case will be some function of y. And we already know that partial of y has to equal n. So then we can differentiate this with respect to y, and we will get 3x squared y squared plus h prime of y, and that, so I differentiated f of x y, derivative of x squared y cubed is 3x squared y squared, derivative of h of y is h prime y, and that has to equal n, which is 1 plus 3x squared y squared. And these two go away, and then we get dh over dy, which is h prime of y, is equal to 1, which means dh is equal to dy, and then if we integrate both sides, we would get h equals y, and therefore our f now is fully characterized as x squared y cubed plus y, equaling some constant c. So we can say the solution of the differential equation is thus x squared y cubed plus y equals some constant c. And this pretty much concludes this problem. Ben, are you there? Any questions on what we're doing?
I got to this. So far I'm here.
Where? X squared y cubed plus. Right, so the partial derivative of that with respect to y has to equal n.
Right, yeah.
And from there you can figure out what your h of y is, or whatever you call it, g of y. Doesn't matter.